And so you have all these numbers already, right? Because we've looked at maximal and resting stroke volume. We've also looked at tidal volume, which would be kind of our normal inspiratory volume versus inspiratory reserve volume, right? So you could actually kind of see how much each one increases. And the way you really do that is through what's called a fold difference, which really all we do is we take maximal divided by resting. Take maximal divided by resting, that'll give you kind of a fold difference, like it can increase 2 times or 3 times or 5 times or half a time. Okay, if you guys are just guessing which one, what A or B here, which one do you think has a capacity to increase more? Okay, you guys are saying. Okay, yeah, we're kind of split. We got about half saying the heart, the other half saying the lungs here. Okay, so if we look at some of these numbers, stroke volume doesn't increase that much, actually. Yeah, maybe somewhere from around 60 at rest to maybe 120 at max. But then if we look at tidal volumes, typically about a half a liter, okay, maybe 500 mils or maybe even down to 300 mils. But we can get that up to somewhere around 3,500 or 3,800 mils. So again, if we're taking 3.5, dividing it by 0.5, that's 7, right? Is that correct? I think that's 7. I don't know which one of the range I used when I calculated 7-fold. But yeah, so that's how you would calculate this idea of a fold change, right? Whereas this one is 120 over 60. That's a 2-fold change, right? It means it doubles, right? Whereas the other one goes up by 7-fold, which is much, much more. And so pretty much we can look at every factor between or every factor in the pathway of getting oxygen out of the air and using it down in the mitochondria. We can look at it with a fold difference thing like this. And really what we end up seeing is that the one with the lowest capacity to increase tends to be the one that is the limiting factor for VO2 max. So we'll kind of continue on when we look at all these other factors, but these are a couple we have so far. So yeah, Alex.
How does the inspiratory capacity translate to an oxygen uptake? Like just because you suck more air in, you're going to get a proportional amount of oxygen.
It's pretty, yeah, they do track pretty well with each other. So the other way to think about it would be when we look at ventilation, which is kind of our equivalent to cardiac output, but on the air side of things, right, where it's like breaths per minute times how much with each breath, right? Whereas the tidal volume, you know, and stroke volume are kind of similar to each other because it's like with each breath or with each beat. Ventilation tracks really closely with oxygen uptake. So when we see ventilation going up, oxygen uptake is pretty much going up in a very linear fashion with oxygen uptake. So it is pretty similar, actually. Yeah. Obviously on a different scale, but they kind of track well with each other. Yeah, good question. Yeah. Other questions on that? Okay. All right. So let's just kind of go back to what we were talking about before, which again, let me just put that slide up so we're all remembering where we were at. We were talking about this Fick equation, right? And we're talking about how each of these factors increases in order to increase our VO2 when we go from resting up to a maximal VO2, okay? We dealt with heart rate. So if you let us through that, we just started talking about preload, okay? And we said that the determinant of preload was venous return, right? And it can be measured by end diastolic volume. So then really what we need to figure out is, well, since we saw preload increasing quite a bit here, right? We saw a big increase in end diastolic volume. The question is like, what causes that, right? So that's kind of where we're heading next. What makes this happen, right? How do we get all of a sudden so much more blood in the heart before it contracts? And so there's 7 primary factors that increase our venous return or that are related to venous return. And those are all related to increase in our end diastolic volume. Okay, so the first one is what's called our muscle pump. Okay, and directly related to that, is our respiratory pump. And really directly related to that also is the fact that our veins have one-way valves in them. Okay, so we'll start with those three first. Okay, so remember when blood goes out into our arteries, goes into the capillaries are so small, they're literally the size of only one red blood cell can get through at a time, right? So they just go through in single file lines. So there's very little pressure inside those capillaries, right? By the time the blood gets over to the venous side, we've lost all of our blood pressure, right? All the blood pressure that was created by the heart that we felt on the arterial side is now gone, right? So we don't have much power to get that blood back to the heart. And so we need help, right? And so these are a couple mechanisms that help us get that blood back. And so number one is the fact that our veins tend to be around areas where there's muscles too, right? And so when we contract muscles, we smash down veins too, right? And that's exactly what it's showing here, right? So we smash down veins when we contract our muscles. And as we start exercising more and harder, we do that more frequently, right? We contract them more frequently and we contract them harder too, right? So we're smashing down those veins even harder, okay? The other thing is when we take a deep breath, we have all these really large veins inside of our thoracic cavity and abdominal cavity, right? Our vena cava, our big thoracic ducts that all the veins are dumping into, right? A lot of those very large veins don't have valves in them. They're just too big for valves. But when we take a deep breath, that closes those, right? Because they're pretty flat, they have pretty floppy walls. They're not like arteries that are thick and muscular, they're pretty floppy. So when we take a deep breath, those big veins get smashed too, right? So that's our respiratory pump. And so when that happens, the blood inside of them gets pushed, right? And so the more frequently we breathe, the harder we breathe, the more we do that, right? So we have muscles contracting more frequently and harder. Our breathing is more frequent and harder. And so we're smashing down all these things and blood's getting pumped back towards the heart, right? And it's really helpful here that we got valves in these because otherwise blood would go both directions, right? But since the valves are there, it tries to go both directions. It hits the valve and then goes the other way, right? And it's kind of making this incremental progress in a vein because once it gets past one valve, it's not going to go back that way, right? It's going to kind of notch up to the next part and keep making that progress back towards the heart, right? So as we start exercising, we increase our muscle pump, we increase our respiratory pump, and the one-way valves are just there. They're just doing their job all the time, but they're helping us do that. Okay, questions on that so far? Okay, the other thing that's similar to this is called the pulse wave. Okay, and that's this one up here. And this is kind of a cool setup in the fact that almost all the time when we have an artery, we have a vein right next to it. Okay, and then we usually have a nerve there too, right? We usually have these, if you guys, if any of you have taken the gross anatomy course, or is anybody in that right now? Yeah. So typically you see that, right? In the cadaver, you see that vein, artery, nerve combo, right? And so the fact that the artery is right next to the vein, every time that your heart pumps, it sends this pulse wave out all the way from your aorta, stretches out the artery, and it's pushing along a vein that whole time, right? So that little pressure that it creates on the vein actually pushes blood back towards the heart too. And so as we start exercising, that pulse gets stronger, it gets more frequent, just like our breathing, just like our muscle contraction. That's helping us push blood back too. Okay. And then the other big one that's really going to help us, sympathetic tone or just activity. So it means when we start exercising, we activate our sympathetic nervous system, right? That's going to cause vasoconstriction. Right, so systemic vasoconstriction is caused by our sympathetic nervous system, okay? But then this also mobilizes our blood pool in veins. Okay, if you look at a pie chart of where all of our blood is at rest, 55% of our blood is just pretty much sitting out in our systemic veins. It's served as one of the functions of our venous side of our vascular system is like, it's a reservoir for blood, right? So, but veins do have a little bit of smooth muscle on them. So when we activate the sympathetic nervous system, we squeeze down that smooth muscle in the veins and we kind of send a lot of that blood that's just sitting out in our veins back into general circulation, right? So we've got a lot more blood coming back. And then we also got vasoconstriction all throughout. So that means all of our blood pressure is higher. That means blood's just moving through vessels faster. Right, so this is just increasing our circulation a lot. Okay, and then we've got two other things that are affecting venous return. One would be our body position. Okay, and then another one would be something called the Valsalva maneuver. Okay, so when some of you people that, or some of you guys that lift weights a lot, you know that you're supposed to not hold your breath when you're doing a big lift, right? And a big reason for that is because when you, and you'll see this in a graph in a second, but when you're bearing down really hard and pushing super hard, you can raise your arterial blood pressure to 400 or 500 millimeters of mercury. Okay? There's zero chance that your heart can produce that much pressure. It just can't, right? So that means there's no way you can open up your aortic valve during that time. It's just not going to happen, right? So your cardiac output is zero during that time, right? So if you hold that for too long, you're going to pass out, right? Because there's no blood coming out of your heart, right? And so that's kind of the same idea with the Valsalva maneuver. You're holding, you're bearing down, you're pushing hard, and that just makes it very hard to get any blood back into your heart, and definitely hard to get it out. Okay, the body position one. When we go from laying down to standing up, now all of a sudden we're fighting gravity. So that just makes it harder to get blood back in, right? And so that one affects our end diastolic volume as well. Okay, so when you guys do the concept map for this time around, is looking at that Fick equation, looking at heart rate, stroke volume, and underneath stroke volume, you got the three things: preload, afterload, contractility. Then we'll look over at AVO2 difference, and you're just going to be mapping out how all of those things increase from rest to max. Okay, so when you do this one, you need to have all these factors in here, but it's definitely important to note which ones are actually changing when we go from resting to exercising, right? So the muscle pump's changing, right? Because we're contracting more, we're contracting harder. Respiratory pump, those one-way valves don't change, but they help in this. Pulse wave is definitely changing because that's getting stronger pulse, faster. And then sympathetic nervous system is being activated. So there's kind of 1, 2, 3, 4 that actually changed. Sorry, that was an earlier star that meant something different. Yeah, so there's really 4 that change when we start exercising. And that's what causes this, right? That's how we get this, is because those 4 things changing. Okay, questions on that? Okay, these next graphs just kind of demonstrate this idea that our body position or our posture really does affect our stroke volume quite a bit. And it's based on that end diastolic volume, right? So let's just look at stroke volume here when we're lying down versus standing up. Right, so somewhere around 90 mLs per beat in this example when they're lying down. Standing up, only about 70, right? So they lost about 20 mils per beat just by standing up. Okay, cardiac output can stay the same, right? So that must mean that we had to change heart rate in order to maintain our cardiac output, right? But this is exactly what happens, and this is why sometimes when you get up too fast and you're dehydrated, you can feel lightheaded or you can pass out, right? It's because it is a little bit of cardiovascular stress just going from lying to standing because of the gravity that your body's now having to fight against, and you don't fill up your heart as rapidly. Okay, questions on that? Okay, so let's look at the second factor related to stroke volume, which would now be afterload. Okay, so we talked about preload. Now let's talk about afterload. Okay, so who's got a definition of afterload for me? Preload was how much we fill up the heart before it contracts, right? What's afterload? Go ahead. It's not, Erica, yeah. But I set you up for that, huh? Because I said preload is this, and then but yeah, I almost do that on purpose because there's so many students that automatically jump to that. So I'm glad you said that because it's a common misunderstanding. So it's not how much blood's left over. It has something to do with this guy right here. Good. The amount of pressure it takes to overcome that pressure in the aorta. Perfect. Yeah. So it's that pressure that needs to be overcome in the aorta to open up the aortic valve. Okay. So what determines this is really just our blood pressure, right? How much pressure do we have in that aorta? Okay. And a good way to measure it would be our average blood pressure over time, which is called our mean arterial pressure, or MAP. Okay, and most of the time, especially when we're at rest, we're in the diastolic phase longer than we are in the systolic phase. Right? So when you look at the equation for that, we have about 2/3 of the time that our heart's at rest, and then about 1/3 of the time that our heart is contracting. So if we want to get somebody's mean arterial pressure, we pretty much get their normal blood pressure, it would be systolic over diastolic, times that diastolic by 2/3, times the systolic by 1/3, and that gives us our average blood pressure over time. And this is what we're getting at with that Wiggers diagram that we'll look at again here in a second. And this idea that we've got to overcome that pressure in the aorta to open up the aortic valve. Questions about this so far? All right, everybody got it? Good. Okay, so this is what I was just mentioning with the increasing arterial pressure. Okay, and we can see this was actually from a study where they measured intra-arterial pressure. Okay, while somebody was doing a leg press at 90% of 1 rep max. Okay, so they're doing like 11 reps to failure, and actually they have an intra-arterial pressure monitor, and they're measuring how much pressure is in the arteries. And you can see with each rep has a little spike in the line pretty much, right? So the first rep, they get up to about 350. By the end, they're getting up to 450 millimeters of mercury in their femoral artery, right? So that's a lot of pressure, right? It's a ton of pressure. Okay, that's not the exact pressure that would be at the aorta, but it's very high, right? And so, like I said before, the heart, there's just no way the heart can produce that much pressure. Our heart can maybe produce 200 millimeters of mercury when we're maximally exercising, but no way 400. It's just not going to do it. So during this peak period of time, that aortic valve is not going to open. It just can't. So yeah. So yeah, if we look at this in terms of the Wiggers diagram, like we had before, and this was just one of the questions that some of you answered on the test, then this dotted line, again, is our aortic pressure, whereas the red line is our ventricular pressure, right? If we're just changing this line to where it's up here instead, something like that, right? Then we change the amount of time that this is open, right? So the amount of time this is open shrinks down by quite a bit, right? So we'll have this amount of opening time instead of this amount of opening time. And so what would that do to our stroke volume? Up or down? Give me a thumb. Yeah, good. So most of you are saying down. So this is going to decrease stroke volume for sure. Okay, now the heart can do some things to try to maintain stroke volume, which would really is just contractility increase, which is one we haven't talked about yet. But in general, your heart rate is going to have to rise quite a bit in order to maintain cardiac output. Right? Okay. Questions on that? Okay, so when it comes to afterload, we got a few things that affect it. Okay, so obviously just our blood pressure, right? And it has an inverse relationship with it. Well, sorry, it has a direct relationship with blood pressure, but the thing I was getting at was that afterload has an inverse relationship with stroke volume. Right, the higher our afterload is, the lower our stroke volume is, right? Because it's harder, more pressure to push against. Okay, but the higher your blood pressure is, the higher your afterload is. Okay, so we'll just say a direct relationship. When somebody has atherosclerosis like this, that means thickening of the arteries. We'll talk about this in detail coming up. But thickening of the arteries, they don't stretch as well, and your blood pressure goes up, right? So direct relationship with that too. The more atherosclerosis somebody has, the more or the higher their afterload is. Okay. Aortic stenosis, same idea. That's when your aorta starts kind of closing in and becoming too thick and doesn't stretch out as well. So that's more pressure to push against. Okay. Hand grip maneuver is very similar to the Valsalva maneuver, but it's just kind of with your arms instead. So you're just like, when you're squeezing down something like this, that creates a lot of aortic pressure as well. So that increases your afterload. Okay. And then the tricky one here, as you go to do your concept map, and as you try to think about this one, is what happens during exercise when you do your blood pressure. Okay. How many of you have taken the exercise testing and prescription class with Dr. Gans? You taken that yet? Yeah. Did you guys do some during exercise blood pressure in that class? Did you guys measure anybody's blood pressure while they're exercising? You didn't do that? Online, yeah. Gotcha. Gotcha. Yeah. Is that what everybody in the same boat? Yeah. Oh, you're right now. Okay. Maybe you haven't got to that part yet, but yeah, typically you'll do an exercise test. You'll actually measure blood pressure during the test. But maybe some of you just know what happens. What would be a typical, let's say somebody's blood pressure at rest is 120/80. What might be a typical blood pressure for somebody when they're exercising hard, when they're running on the treadmill 7 miles an hour or something like that? Any ideas? Would it be higher than that or lower than that? Higher, yeah, for sure higher. Typically what we see is systolic blood pressure is going to go way up. So we might see something like 160, even up to 180 during intense exercise. But diastolic, interestingly enough, is either going to not change, I'll put this kind of arrow, or go down just slightly. Okay, so maybe just a little bit down. So we might see something when somebody's at max or at an intense exercise, maybe their blood pressure goes from 120/80 to like 160/78 or something like that. So it might go down a couple millimeters of mercury on the diastolic. Okay. But if we calculate mean arterial pressure there, right? So our mean arterial pressure was 1/3 times systolic blood pressure, 2/3 times diastolic blood pressure, right? If we take, if we do our 160/78 and compare that to 120/80, which one's going to have a higher mean arterial pressure, exercising or resting? We don't even have to calculate it, right? But what do you guys think? Definitely during exercise, right? The confusing part and why I'm spending some time here is because the book doesn't clearly state this at all. What the book says is that there is some, because of the fact that there's a lot of vasodilation when you're exercising, that actually lowers your total peripheral resistance, which just means you have some bigger vessels. But the other side of that is all of your blood vessels besides the ones that are vasodilated are constricted, right? Because that's what your sympathetic nervous system does. So overall, your blood pressure is going to be higher. So then the bottom line with this is, does this help increase our stroke volume while we're exercising or not? Talk about that for a second with the people on your team. Is this helpful for increasing our stroke volume or not? When your mean arterial pressure, when your afterload goes up, is that helpful for increasing your stroke volume or not? So give me a thumbs up for helpful, thumbs down for not helpful. Okay, we got some not helpfuls, some helpfuls. Not shares. Not helpful. Okay, we're kind of mixed up. Why did you guys in the back think helpful?
I think another because, as we mentioned earlier on the increase is like a slight vasoconstriction constriction, typically increases the the preload.
Mhm.
And so yes, it does increase afterload, the blood pressure. So overall, I think that preload is really better.
Yeah, that's a good way to put it. So my answer to the question would be that as far as the change in afterload that we see here, maybe I need to be more specific with the question. The fact that afterload goes up makes it a little harder to get blood out of the heart, right? So that directly, the increase in afterload directly has a little bit of a decrease on stroke volume. But like John just said, which is totally true, is that also by increasing our blood pressure, we get higher end diastolic volume. And so that helps our stroke volume. So it's kind of both ways, but when we're just looking at the effect of the afterload itself on stroke volume, then that actually has an inverse relationship with stroke volume. So yeah, kind of confusing for sure, but in general, when we look at afterload, we think of this one really not directly helping our stroke volume, but the increase in blood pressure is necessary for end diastolic volume too. So yeah, so there's really the three factors: preload, afterload, contractility. We tend to think of preload and contractility going up, which helps our stroke volume go up, and then afterload goes up, which kind of fights against our increase in stroke volume directly right there at the aorta. And so that's kind of the way to think about it. Okay, questions on that? Okay, so let's talk about the third factor, which is contractility. And so contractility is the force of our heart's contraction. Okay, the thing that controls this is how much sympathetic nervous system activity we have. Okay, and the way that we measure this is through that measurement of ejection fraction. Right, ejection fraction was our stroke volume divided by end diastolic volume. If we want to turn that into a percentage, we times it by 100. Okay, again, this is just like the percentage of the blood that's coming out compared to what we started with. Okay. All right, so that one, when we look at that in terms of these Frank-Starling curves that we looked at before, again, that was preload or end diastolic volume versus stroke volume. We know that as preload goes up, stroke volume goes up, especially in the early parts of this curve. It goes up a lot. Stroke volume goes up for a little bit more end diastolic volume. But there's also this other factor that this might be our midpoint. That's not a lot of sympathetic nervous system activity. But then all of a sudden, if we increase sympathetic nervous system activity for that same increase in preload, or for that same amount of preload, we get a lot more stroke volume, right? For the exact same amount of preload, we get more stroke volume simply because we contract the heart harder, right? So which volume, as far as if end diastolic volume is the same, right? Which one had to change to give us a higher stroke volume? If we're just comparing this point to this point, same end diastolic volume, different stroke volume. There's only one other volume involved in the equation, right? So which one is it and which way did it go? EDV stays the same. Say it again. Decrease, good. Yeah, so so the end systolic is lower, meaning that there's less blood left over in the heart after the heart contracts. And that's a function of how hard the heart contracted, right? It emptied itself more. Right? So this would be because of a decrease in ESV. Okay, and same thing with ejection fraction. If our end diastolic volume is the denominator of that equation and stroke volume is the numerator, obviously stroke volume is going up, end diastolic volume doesn't change, that's going to give us a greater percentage of the blood that came out. Okay. So why this happens is it's all about increased calcium release in the cardiac muscle. Okay, sympathetic nervous system activity activates the sarcoplasmic reticulum even more in those cardiac muscles. It releases more calcium, right? So we get an increase in actin, myosin binding, right? And that's going to give us more force when those sarcomeres shorten because we got more myosin heads helping us out. Okay, questions on that? Okay, so we've got a couple of things just to look at briefly, just to kind of get you ready for the TBL day. That's really what the last few slides here are. And so we've talked about all parts of the thick equation except that AVO2 difference side. Okay, we'll skip this question for now because we'll deal with this directly on the TBL day. One thing I want to make sure you understand is this idea of partial pressure. Okay, partial pressure of a gas is really all we do to calculate that is if we know our total atmospheric pressure, which at sea level, it tends to be somewhere around 760 millimeters of mercury. And then if we know our percentages of the gas in the atmosphere, then we just multiply those by each other, right? So to find out the partial pressure of oxygen in our air, we take our total atmospheric pressure, times it by this percentage of oxygen, right? Which we need to put it back in this decimal form to do that. So we would just times it by 0.2093 or 0.21 is close enough. And that'll give us of the total air that's on top of our heads, which is what the atmospheric pressure is, right? Of that, X amount is contributed by the oxygen in the air, right? If we take that 79% CO2 or nitrogen of that total amount of weight on our head, 79% of it's from nitrogen. So we just do those calculations, right? So 600 of that 760 is from nitrogen, about 159 of that's from oxygen, and about 0.2 of that is from CO2. Okay. Everybody got that? Looks like you done it, John. Okay. The way that we'll look at that, and I'm going to skip this one for now, but the way that this will make sense, and we'll spend some more time on this during our TBL days as well, is when we're getting oxygen all the way from the air, all the way down to the mitochondria, again, all of those little steps, we have to have a drop in the concentration of oxygen every single step for oxygen to move, right? It's just going from higher pressure to lower pressure every step, right? So going from the air to our alveoli goes down, alveoli to the blood goes down, blood to the interstitial space, the space between the cells and the blood vessels, from that space to our cells, cells to the myoglobin, finally myoglobin down to the mitochondria. We've got to have a step each way, okay? And we'll talk a little bit more about that, some of those questions during the TBL day. Yeah, we're out of time there, so I'll probably, after you do the quiz, I'll kind of get back into a couple of these. Hold on, let me just do one thing real quick, guys, because this will be important for you understanding the quiz on Friday. This AVO2 difference, again, this is the arterial blood, this is the venous blood. Okay, when we look at the blood coming out of the heart, it's coming out of arteries, right? Those are going to split off into little capillaries and then go back to veins. Okay, so this is the venous side, this is the artery side. Okay, if we got 100 milliliters of blood going in and we only got 50 mils, oxygen, 100 mils of oxygen in the artery, only 50 mils left over in the veins, that means that we extracted 50 mils of oxygen when it went through those capillaries, right? That's what the AVO2 difference means, is just that difference between how much oxygen is in the arteries versus how much is in the veins. And this is really going to be dictated by how much oxygen can diffuse out of the capillaries and be used by the mitochondria. All right, so that's kind of what you'll get into with some of the stuff you study for the quiz. I just wanted to kind of draw that so you can kind of conceptually see what that's talking about there. Okay. All right, guys, we'll see you on Friday.